You see the question, and in this question there are two functions, but when you see the options you have to face four functions. I show you those functions here. The first function is the first function that you saw in the question, that is our f. The second is g, that function also is on in the question, but the third one is the composite function, and the fourth is GOF, the second composite function. So we have to check the Riemann integrability for these four functions. So let us move and check one by one. Okay. So the first function is our fx, and we check this function for Riemann integrability, that is, it is Riemann integrable or not. So you know, in that integrability test we take a large number of intervals and we find LPF, UPF, the lower limit and the upper limit. If both tend to the same value, then we say that the function is Riemann integrable. So let us take a interval. Here is the interval. You see the interval 0 to 1, 0 to 1, and if we divide this interval by we divide this in let us take the number of intervals to be a. So this can be, as you see, here will be 0, here will be 1, here will be 1 by a, and here will be a minus 1 by a. Okay, so and the remaining intervals here we can make dots. Now we go for the value. That means we take the first interval, the length of first interval is 1 by a, and also you should assume that a very large prime number. Okay, a very large prime number. So the first interval I show you in red. Here is the first interval, the length of first interval. So this is 1 by a, and I write that here and multiply this with the value, the max value of fx in this interval. You see fx here, and that interval, for that interval the max value of fx is 1. You see here 1. So I multiply this the length of this interval with max value, that is 1. Thereafter we put the sign of the plus sign, and thereafter we take the next interval. The length of the next interval will be 1 by a. Okay, and again we multiply this with the max value of fx in that interval, in the second interval. If you observe, then for that we have to take this one. Okay, and in that, since the you see the limits 0 and 1, then in that interval, if there are two cases. The first one is it may be a rational number, and otherwise it may be an irrational number. You know, there are infinite rational numbers and irrational numbers between the two numbers 0 and 1. So if it is if you considering irrational number, then you see it is 0. Okay, if you are considering, but we have to take the max value, so we cannot take 0. So we take the value according to this function. I show you in blue enclosure. Okay, you see, and this is 1 by n. For what? For this, if x is 1 m by n, and since we have taken this this a to be a very large prime number, so whatever be the rational number, okay, whatever be the rational number, suppose it is 4 by n, then we take 1 by 5 the value of function fx. So here we do not know the value, we take a general value, and for that we here take 1 by n, okay, the largest value, because 0 is the smallest, 1 by n is the larger value, so we take the larger value. And for going for the third in the same way, here will be 1 by a into 1 by n, and the last interval 1 by a into 1 by n. Okay, so when you tend a to infinity, okay, if you tend a to infinity, then suppose you know that there are many rational numbers such as 4 by 5, 4 by 7, so these n may be different, okay, not the same, may be different. So for preciseness, we can place here n1, here n2, here n3, whatever be the values of n1, n2, n3. If you tend a to infinity, a very large number, then this whole thing is going to be 0. Okay, so what we get so far? We get that if we take the length of sub interval and multiply this length with the max value of fx in that interval, then it will be 0. If the number of intervals we take a large number, so we are getting 0. Now we do the same. Okay, we do the same, but this time we do the same. It means that we take the first length of first interval, it is 1 by a, okay, and but this time we take the value of the function to be the lowest, and in that you see lowest will be in case of irrational number, it is 0. So in this, for this interval, the minimum value is 0, and in the same way the other, for the remaining intervals you will have to put 0, and in this case as well you are getting 0. So in both the cases we got 0. What are the cases? Cases are, first case is when we take the length of subinterval and multiply it with the max value of fx in that interval, then we are getting 0. If we tend the number of intervals to be infinite, or you may say a very large number. And in the second case, when you take the subintervals, the length of subinterval, and multiply with the minimum value of fx in that interval, then you are getting the same 0. So the function fx is Riemann integrable. So we tested our first function. And now let us check for the second function, that is our gx. Okay, so I erase what I have written on the screen. Now I go for the second function, and for the second function as well I take the interval is the same, you see, the same, you see, yeah, the interval is the same. So here will be 0, here will be 1. Okay, now this time take the number of intervals to be n. Okay, so here will be 1 by n, here will be 2 by n, and so on. Here the second last will be n minus 1 by n. Okay, now we do the same. Okay, we take the first value means the length of this first interval. I show you in red, this is the length of first sub interval, and the value of this one is 1 by n into the max value of gx, this function gx in that interval, and that is 1, obviously 1, because it is 0 at 0. But whenever you take the value other than 0, for that it is 1, so the max value will be 1. Okay, so here will be 1, and for the remaining intervals, that is the second sub interval, it is also 1, and for all, okay, 1 by n into 1. So what you get n minus 1 by n. If you add, then you get n minus 1 by n, and you know this 10 to 1. If you turn n to infinity, then you have this limit as 1. Now we do the same, but for this time we take the value of gx in each sub interval to be the minimum value, and see what do we get. Okay, so this time we take the same interval, the first sub interval, its length is 1 by n, and this time in this interval we take the minimum value, then it is 0, obviously it is 0 at x equals to 0. So we multiply this with 0, and the length of second interval, the length of this sub interval is 1 by n, the same, and this time we have to multiply it with 1. Okay, the remaining intervals will be multiplied by 1, and if you tend in this sum, if you tend n to infinity, then you will again get the same thing, 1. So in both the cases we got the same limit, and that limit, this means that the limit exists, and this ensures that the function g, the second function in the question, is also a Riemann integrable. Okay, now we go for the third function, that is not in our question, but those two composite functions you see in the options. So we go for the third and the fourth function. The third function, let us see, here is the FOG. Okay, so the third function is our FOG. So FOG means this function fgx. Okay, and it means that we have to put the value of gx, and you see for x equals to 0 it is 0. Okay, so here will be f0 for x equals to 0, and for other, that means other than x equals to 0, for that it is, you see, 1. So here this will be equals to f1 for x is not equal to 0. And you see f1 here, you see f1 with this you can get f1. If m and both are 1, then x will be 1, and for that f1 will be 1. Okay, so here will be 1. So and notice that f0, if you see here is the here is the f0. If you see f0 you see here x is 0, so f0 will be 1. So this is also 0. So if you summarize this whole messy thing, then you have fgx equals to 1 for all x. This is a constant function, and you must know that every constant function is a continuous function, and so it is Riemann integrable function. So our function fgx is also a Riemann integrable function. So now I go for the last function, that is in our fourth option, and that function is zfx. Okay, zfx. Okay, so let me write it at a new place. Sorry, here I write zfx. Okay, so zfx, z, and when I put x equals to 0, here is our fx function. You see, here is the fx function. So we do the work according to this. And first you see x is 0. For x is 0, the value of function is 1. So here x equals to 0, and you see f0 is 1, and here I write x equals to 0. And g1, if you observe, then g1, you see g1 is 1. So this function is the value of g of x will be 1 at x equals to 0. Now I write the same, but for this time we take this one. Okay, the second condition. So this time x equals to m by n. It means that for a rational number there are 3 conditions only: 0, rational numbers, and here is the third one, irrational numbers. Okay, so this time I work for the rational number, and for that you see that here it is 1 by n. I show you in red. Here is 1 by n. Okay, so I here put 1 by n. 1 by n. Okay, and g1 by n. Obviously 1 by n is not equal to 0, because n is a natural number, and you know any natural number is not a 0. So for that we have to take this value. g1 by n will be 1. So here it will be 1. For what? When x equals to a rational number. And the third one, g of x. Again I type the same, g of x equals to, this time x is I have to take x an irrational number, you see here, and for that fx is 0. So I put here g0, fx equals to 0. Fx is 0 here, you see, fx is 0. So g of x equals to g0, and you see here g0 is 0. Okay, so this will be 0. So if we summarize this whole messy thing, then what we get? We get that, I show you. We get that g of x. Okay, g of x is 0 for x equals to 0, and g of x equals to g of x equals to 1 for x equals to rational number, and the same g of x equals to 0 for any irrational number okay, x. Okay, so it is very easy to check this function g of x is not a Riemann integrable function, because you do the same as I did for the function fx and gx. If you do the same for this function, suppose this function is hx, so if you use the same process as I did for fx and gx initially at the starting of this video, then you will get the two sums, the two limits. You will get the two limits different. Those two limits will not be equal to each other. And one more thing, you see this function is in a nutshell. We say that hx is 0 when x is 0, hx is 1 when x is rational number, hx is 0 when x is an irrational number. You can find in any book or even in YouTube. This function is not a Riemann integrable. And one more thing, you should first try yourself. You do the same as I did initially in this video for fx and gx. You will find that the two limits are not the same. So this function g of x is not a Riemann integrable function. So let us now move for the options. Here you see the option. So we prove that our first function f was Riemann integrable, g was also Riemann integrable, fgx was constant, so Riemann integrable. But the last one, the function g of x, which I denoted by hx, is not a Riemann integrable function. So our correct options are A, B, C and C.